All right. Awesome. We still got some time. So good. We're gonna go through. So sampling. So I don't know. I don't know. I know in California is Costco. Is it nationwide? I don't know. UK. Nadine, do you know what Costco is? Or like, okay, cool. Like I actually was thinking about this. Like, I don't know.
It's
Costco sampling.
international, I guess.
Okay.
We get it
All
as
right. Cool.
well.
I remember it being like Price Club. Anyway, so cool. So you guys all know Costco samples, right? So sampling. I actually think it's a really great example of like saying sampling. Like, what is samples? It's like, oh, well, when you have a sample of something, you're kind of like taking a bit of something to test something out, right? It's not the actual product. It's not the full like box of things. It's like, oh, you're taking a sample to get an idea of what you want for the whole, right? So that's kind of like a good idea of sampling. It all kind of fits together. I'm for sure there's like some linguistic reason why it's called samples. Okay, so why do we do samples, right? So the real reason why we do samples is our view of the world isn't perfect, right? We don't have perfect information, right? Life doesn't have an answer key. We just can't just look up in the back of the book. You'll hear people talk about like the population, like true population mean, true population standard deviation, the true population distribution. There's literally very few times we can actually say the true distribution, true information about the full population. So what do we do about that, right? Well, what we can do is we can't look at the whole population. And can some people give me some reasons why we can't feasibly look at the whole population? Like, what are some like concrete reasons why?
Uncollectible.
Okay, so Kiva said, what's that?
Uncollectible.
Collectible?
Uncollectible. Like you just can't put all that data together. Just impossible.
Right. So yeah, sometimes it's just too many things, right? It's just impossible to collect all that information. And then I saw Jessica too.
Yeah, I was just going to say it would take too long. It would cost too much. We're not able to reach everybody.
Yeah. So yeah, I like that you said reach everybody too. One is like, how do you reach, let's say you want to know the weight of all people in the world. Like that seems like one's like, technically you could do it, right? Maybe this is possible. So that's not maybe necessarily uncollectible, but it's other like logistics. Like how do you make sure you weigh everyone? What does that mean even? Like, do you weigh them all with the same like scale? Like, do you just kind of give out this information? There's a lot of information on this. Also, part of it is it's expensive, right? Oh, cool. And I got a little chat message. Someone just saying hi. Yes, U.S. Census. Perfect, Edward. So U.S. Census was actually the exact purpose of this is that the U.S. Census, which is 2020, which for the record, I'm an advocate for saying, yes, you should reply to the U.S. Census, be as accurate as you can, because otherwise it costs us a lot of money as taxpayers too. Then you don't have to worry about it since you don't have the U.S. Census and everything. But big thing about U.S. Census is that we're literally trying to collect all this information, accurate information about people. There's a whole bunch of reasons why you shouldn't have to worry too much about like, oh, do I give this information? They actually are doing something called, oh my gosh, differential privacy. I don't know if anyone's heard of this before. But look it up, differential privacy in US Census. It's really interesting. The idea is basically you can give information, but when you actually collect the statistics, you can't actually easily pull out individual information from it. But big thing about the US Census is that it's expensive. We only do it every 10 years. And a big reason why it's so expensive is because we literally have to get as accurate as possible. That's the law, how it's written. So those are some reasons why we can't do population versus just being like, this is a pain, a lot of time and all that stuff. Okay. Yeah. Oh, and also the last thing, we don't need it. We don't need all the full population to actually get all the insights. And that's really what sampling comes through. So I'm gonna give a quick scenario. It's a really basic scenario. I think I came up with this when I was hungry. So imagine a school and we want to know if they prefer chocolate over vanilla, right? And so you're like talking to, they'll say like elementary school. So like, kindergarten, first, second, third, like 5-year-olds all the way to like, I don't know, 13-year-olds, right? How many students would you really need to ask until you get the right idea of the school, of like if they prefer chocolate or vanilla? So obviously I'll just straight up say, if you ask everyone, duh, right? You'll know about the whole school. But we're gonna say, well, we wanna make this as quick as possible. We don't have to talk to every single child in the school. Obviously I will say is that you probably don't wanna talk to one child, right? Like there's no way you can encapsulate all the information just by asking one child, right? Like you basically would either get chocolate or vanilla, and that's pretty much all the information you get. So how would you guys design this? I want you to think for like, 20 seconds, just think about like, how would you actually get this information? Like, I don't know, you're a teacher or something, or, you know, you're actually a student. It's like, I want to learn about the whole school. What would you do to make sure you get this information? Or how many people would you ask? How would you design this? Yeah, Jessica, go ahead.
So it would depend on how many kids were in the whole school and, you know, different classrooms and grades. I would want to have like enough sampled boys and girls, all different ages, all different classes. And I don't know how big the school is, but a pattern would probably emerge probably sooner, but I think it'd be good to have at least like 30 to 50 students. Yeah.
Okay, so like 30 to 50 students. And asking a little bit deeper here, how do I get these students? Like 30, 50, like you say, let's say you say 30 students. And I just go say, all right, 30 students, and I grab all of second grade. Is that?
So I think I would want to know, you know, I would try to make it even between the different grades, classrooms. So depending on how many there were, maybe go into the classroom and again, keep it even, like boys, girls, different classrooms, different grades, but try to keep it, you know, a good representation of the whole.
Okay, so you're thinking more in the sense that like you have 30 students total, but like you get 3 from this grade, you know, 3 from this grade, 3 from this grade, 3 from that grade, right?
Yeah.
Yeah, so that's definitely one strategy. That's called a stratified sample,
Right.
and you can definitely do that. And Alvera, I saw you unmute, so did you have another method or addition to that?
No, it would be random. I want to take random samples, run around and decide on a number that you want, and then just grab random samples. This way, a little bit of any bias you might have or whatever won't interfere with in it.
Yeah, and so there's actually, this is great that Alvaro, thank you. Randomly sampling, just like literally just say, all right, I'm gonna randomly, you know, random, you know, you have to figure out like what exactly you mean by random. Probably something like having like the list of students that, like on a list and literally picking a random number between 1 to however many students there are and making sure that's actually random, right? So that's a whole different story. But those are 2 different strategies, right? Jessica said like, all right, let's split them up into different parts. Alvaro was saying, hey, let's do a random sample. And both of them have actual real reasons why you want to do this. In general, we tend to go towards random sample just because it ends up being cheaper. However, I will say is that it's usually hard to try to get a true random sample. So one thing, for example, you'd probably want to go talk to every student, or not every student, but talk, if you're going to random sample, make sure you actually go and ask them and make sure they give you an answer. Because if you did something like you sent it out to, like, let's say you send it in the mail to students or something like that, some students might not respond back to you right away and stuff like that. For example, let's just pretend chocolate lovers love chocolate so much that they have to express that they need to tell everyone, hey, I love chocolate. And so those are the people who are going to make sure they fill out that form and send it back to you, right? Where the vanilla people are like, you know, I like vanilla, but I'm not going to like stress anyone else, imposing saying like I love vanilla and like over chocolate and stuff like that. So then maybe they're less likely to really care about this survey and stuff like that. And so you have to make sure you actually random sample. And this is actually a big issue with getting statistics. Stratified samples can be really useful for very small groups, or if you believe the groups are in fact very different. So for example, let's say this school has only, like for some reason, 5 third graders, right? And let's say we assume that grade really matters. Maybe the older you get, like the more you like vanilla or something like that. Let's just pretend that's like a real thing. Then you'd want to make sure that you do represent those people in that, you know, in that school, because you might completely miss them over. Versus like if you have a huge, like say this first grade class is like 70 kids and like there's only like 100 kids like in the whole school, like you're just going to get basically find out about the first graders, which might be arguably what you want. But if you're trying to figure out more detail, you might actually want to do something stratified. So one thing I'll say is that there's no perfect answer in like exactly how to sample. It all depends on context and what you're doing. So this is where I will say is usually random controlled samples are usually the best thing, and usually are considered really high up there on the scientific, you know, like board of like, oh yes, like amazing data. However, it's not always the most appropriate thing. And sometimes, you know, sometimes I hear people say like, oh, stratified samples, like, oh, like this wasn't like, you know, this wasn't well done because didn't do a random sample. It's like, well, you know, depending on the situation, it might actually make more sense to actually break them into different groups. Okay, so cool. Any questions on that? I think that was, it's kind of nice to play with these like really simple examples because I think like even like something really small like this can actually add a lot of like, well, how do you do this? Okay. Cool. So let's see here for sampling. So from a sample, we can get something called point estimates, right? And these point estimates basically are estimates of the population parameters. So the important part is that no matter how you sample, you'll never know the true population directly, right? You'll never know if you got like maybe you're a little off or how off you really are. We can kind of do estimates, and there's actually different something called estimators, where these estimators might be more biased or less biased depending on the distribution. So one thing, for example, is, using a mean, okay? So we talked about skewedness, for example. If you use the mean and the distribution is a normal distribution, getting the mean, you're probably going to, get a good idea. But if you're right skewed or left skewed, right, positively skewed, negatively skewed, the mean is going to follow that skewness. And that might not be the best thing. So some estimators like the median, for example, which is going to basically say 50% are like less than this value, 50% are greater than this value. Those ones are more robust against, skewed distributions. And so those are kind of things to consider and stuff like that. With an exponential distribution, you almost always are going to get the very, like if the exponential growth, you're always going to get that very large side on the right, where it's basically increasing huge amount. So you have to kind of consider like, well, what is the whole point of me doing this sample? So what's really cool though, is that this kind of a little hint to central limit theorem is that if we actually get the sample means, we can actually get a normal distribution. So we can actually turn whatever distribution we started off with into a normal distribution. Okay. So I'm just gonna kind of skip over this part, but like considerations, you can probably think of all the different things we have to talk about, different biases, survey bias, survivor bias, all these different things that could influence your assumption of, especially if you're doing random samples, assuming that's actually random and that they're independent from each other. You wouldn't want to just talk to your friends because obviously that's biased versus, saying a larger population. You also don't want to just send in surveys or, user input and stuff like this. And you'd be surprised, a lot of data starts off with this way. And you have to kind of go through and say, a lot of data is not independent, where like there is bias in there, and you have to determine, is this bias enough for me to discount all the things I'm looking at this data or all that stuff. So one, for example, with COVID-19, especially here in the States, is we don't necessarily test everyone who potentially has COVID, right? And so the thing about that is that we're probably only knowing confirmed cases of people who are very severe, or at least on that end of the spectrum where they're severe enough where they feel they should be tested. At least that's what here in the United States. That is a bias that's put in there. Now, it doesn't mean you can't get useful information out of it. It's just that you have to realize, what is this real information describing? And for example, some of this information might be like, hey, this might actually be describing information of how many people were actually tested. And in fact, you can kind of determine a little bit too, based on what you know about the disease, what you've already seen a little bit, and some thinking about how exponential growth works, you can actually estimate saying, well, based on how many deaths or how many severe cases that we actually have positive, how many people do we actually think are in the population? And you can actually do these values. So just because data is biased in some direction doesn't necessarily mean it's not useful, but you have to be considerate and be a little skeptical of exactly how does this affect your analysis. Okay. Cool. All right, so some coding examples. Hey, code, remember code? We're just quickly, I'm getting the Titanic data set. Have you guys seen the Titanic before? I think it was one of the labs, right? Yeah, so I'm gonna pull this up in here. So just kind of quickly show you guys, right, the Titanic data. We have some information. I'm just gonna pull up the ages specifically, so you can different age and stuff like this. And I'm gonna just drop out the nulls. So I'm gonna take all ages, I'm gonna drop that, null, right? And we can see the average of all 714 people, not a huge amount of people, is 29.7 years old. Okay, so that's the average, right? And so honestly, if you know nothing else, like if we only knew there was a person on the Titanic, you would say, well, what's their age? Like, oh, they're probably about 30 years old, right? Will that be true? No, right? You can see right here, this person's 38 years old, right? There's definitely some children on here, for example, that would not, would be much younger than this or much older and stuff like that. So the thing is though, on average, like if we took our best guess, we probably would get something like most people would be pretty close to 30 years old. Okay, so that's our true population. So kind of looking at a little bit, it's like, okay, we know what the real answer is. Let's say we start off with a random sample. So I'm just gonna walk through this code a little bit since this might be the first time really seeing this. So as we saw, like all ages, which is just basically, if I look here, run this here, yeah, all ages is basically just this age is a series, right? So you need the NumPy array. I'm just gonna sample. I'm gonna sample 100 like I'm going to sample from that 714 people and pull out 100 ages, right? I'm doing a random state of 27. Doesn't really matter what the number is. Basically, it's just so it's consistent. And I like the number 27 just for it. So I'm just putting it in there. And then what we're going to do, we're going to say, okay, let's find the mean, the means of that sample. So just to kind of show you guys what this looks like. If I run this guy right here, mean S, what's really nice is because this is an NumPy array, you'll see is that I get the mean of all those samples. Okay, so it's like, okay, well, how, like we can see here when I take the sample, sorry, of all the samples of this sample, we have 100 different individuals, right? And so that mean is about 28.7. Hey, that's not too bad, right? That's pretty close to the actual like number here. And so we can actually say, well, how close this is actually. And so I actually create a little function here called calc percent error. So I'm kind of throwing you guys for a little bit of a loop of like, what's going on here? Because this is a lambda function, as you notice. And remember, lambda functions taken inputs, and then on the right side is the outputs. So I have pop mean, sample mean. So that means it's going to take in pop mean, sample mean. This could have been X and Y, but I'm just running it out so you can see a little bit easier. NP.absolute of sample mean minus population mean divided by population mean. And then I'm just actually calling this, I'm saving this into this guy. I'm sorry, some other question? No? Okay. So this actually is a function right here, and actually I'm saving this as a function. So just kind of show you guys what this looks like. If run this guy. Elephants. Okay. Calc percent error. You can actually see this as a function. So what's really cool is like I now have a real function in here. So now I can actually call this function, and I can actually get the percent error. So I can get this percent error from the mean of the sample, and I can see the percent error is, oh, I remember I renamed this. This should be age mean. Sorry, I was playing around with this earlier. There we go. So we can see the sample mean was 28.7, which is a percent error of 3.384%. So basically it's about 3% off from the population mean, which, you know, depending what you're talking about, that could be really good. That could be like, ooh, that's not great at all. In general, it's like, oh, that's pretty close. Okay. And so this is how we can kind of use sample to kind of estimate what the true population is. Now, this is where you should kind of scratch your head and say, wait a second, Victor. Like, you should be skeptical. How do you know the sample is going to be estimating the sample mean? Or sorry, the population mean? Can we know? Yeah, I see a head shake from Akiva. I see some people going, like I don't want to answer because I think Victor's going to try to trick us. Yeah, so basically there really isn't a strict way for us to know for sure the sample that we pulled actually is going to be representative of the population. Okay, and you can think about this like if you imagine the distribution, for example, let's say if I just go, let's see here, all ages dot hist. No. Run that again. There we go. I didn't do it in line. So you can see here, this is distribution. So you can see here, like this is the average right here. It's kind of skewed off to the right. So maybe the median would have been a better view, but it'd be about there. But you can imagine, what if I just by pure chance, just like flipping a coin like a bunch of times, what if I got a whole bunch of people that were on this tail end right here? I would say that from the sample means like, oh, wow, people are pretty old on the Titanic, like 65 years old, you know? It's like, I was like, wow, I didn't expect that. Like, this is so crazy. And I just been by the chance that you just happen to sample across, you know, just this extreme end, or you can see it on this end too. So this is where you have to be careful. I'll be like, hey, just because I get the sample doesn't necessarily mean it's going to be representative of the true population. And so this is where you say, well, okay, then what are you supposed to do, right? And what's kind of cool is that we can actually work backwards, because usually we don't know the actual answer, right? We can actually go back onto that. And this is actually our next part. And I'm seeing what time it is right now, so kind of going through. We'll kind of say this on for activity maybe next time, but it's the central limit theorem.